Welcome back. Last time we defined the stress tensor by considering the components of the tractions acting on faces normal to our coordinate axes. Today, let's consider tractions acting on an arbitrary surface at point P with vertices Q1, Q2, and Q3 on our x1, x2, and x3 axes. The traction acting normal to the surface is T superscript n, and multiplying that by the area of the surface, delta S, will be the force. N is the outward normal to the surface. And if we were to look at the back side of this tetrahedral volume and consider that there are reaction forces on each of these faces, then we could label them minus T1 times delta S1, the area of this triangle, on the face whose normal is minus E1, minus T2 delta S2 on the face whose normal is minus E2, and minus T3 delta S3 on the face whose normal is minus E3. So again, N is the unit normal to Q1, Q2, Q3. Delta V is the volume of the tetrahedron O, Q1, Q2, Q3. Delta S is the area of Q1, Q2, Q3. And delta S1, delta S2, and delta S3 are the areas of these individual faces. So delta S1 would be delta S times the cosine of theta 1, or N1 times delta S. Delta S2 would be N2 times delta S, and delta S3 would be N3 times delta S. Now, let's assume that equilibrium holds not only for the body as a whole, but for any individual small part of the body, including the arbitrary tetrahedron O, Q1, Q2, and Q3. So equilibrium says that the sum of the forces is 0, sigma F equals 0. So that means that minus T1 times delta S1 minus T2 times delta S2 minus T3 times delta S3 plus Tn times delta S equals 0 for the body in equilibrium. And then knowing that delta S1 is N1 delta S, delta S2 is N2 delta S, delta S3 is N3 delta S, we get minus N1 T1 minus N2 T2 minus N T3 plus Tn times delta S equals 0, which means that Tn must equal T1 times N1 plus T2 times N2 plus T3 times N3, where T1, T2, and T3 are the tractions on these faces, N1, N2, and N3 are the components of the unit normal N. In other words, the traction vector T equals Ni Ti, and from our previous definition, Ti, the tractions acting on each of the faces, are Tij, Ej. So this therefore gives us that the normal tractions acting on the surface with unit normal N, T, is equal to N times T, or in component notation, Tj superscript N equals Ni Tij. And this is Cauchy's formula. This is the general equation defining the stress tensor. And you'll recall that we described a tensor as being defined by two vectors. Well, we now know that the two vectors that define the stress tensor are the unit normal vector N, defining the surface on which the tractions act, and T superscript N, the traction vector acting on those surfaces. And Cauchy's formula states that the traction vector T is equal to N times the stress tensor T, or in component notation, the jth component of the traction equals the ith component of the unit normal times Tij, which shows that the stress tensor Tij, its first index is the index referring to the surface, and its second index is the index referring to the component of the traction. So we've learned before that the stress tensor resolves the components of the traction with respect to the surfaces, and we can now see that in this compact form. So in summary, Cauchy's formula defines the stress in terms of the traction acting on the surface with unit normal n, such that T superscript n equals n dot T, or the jth component of T equals the ith component of n times the ijth component of the stress tensor. This is called Cauchy's formula, and the stress defined this way is called the Cauchy stress tensor. If we were to write this out in matrix notation, we would say that the three components of the traction vector acting on the unit surface with unit normal n is equal to the 9 components of the stress tensor times the unit normal vector. Now notice that I changed the order of this formula here. That's because this formula is equivalent to, in matrix notation, T equals T transpose n. But since we've already seen that the stress tensor is symmetric, then that's the same mathematically as T equals T. However, it's worth remembering this original form of the formula, even though the stress tensor is symmetric, because it helps us understand which index of the stress refers to the area or the surface and which refers to the component of the traction. And then just to remind you of our original earlier definition of the stress was that Tij equals Ti dot Ej. This is just a special case of Cauchy's formula when the unit normal vector n is the unit vectors of our coordinate frames Ej.